Hello students, welcome to Unit 8 Notes, Section 5-1. This is our first lesson using distance learning, so I'll try to make it as quick as possible. The first thing we'll start with is a warm-up. So you have a train that's traveling at 80 miles per hour for 5 hours. How far does it travel? So most of you would have done 80 miles per hour times the 5 hours, and you get a total of 400 miles. And if you want to look at it in terms of your units, you have 80 miles per hour, times 5 hours. And you'll notice that the units actually reduce to be 1, which leaves you with a total of 400 miles. Oops. All right, number 2. A truck travels at an average speed of 48 miles per hour for 3 hours. How far does it travel? So we'll do the same thing. We'll do 48 miles per 1 hour. We'll multiply that by 3 hours. And we will get 48 times 3, which is 144 miles. All right. Beginning at a standstill, a car maintains a constant acceleration of 10 feet per second squared for 10 seconds. What is the velocity after 10 seconds? Give your answer in feet per second and then convert it to miles per hour. So the first thing we're going to do is we'll take our 10 feet per second, 10 feet per second squared, and we'll multiply that by 10 seconds. And that we will knock out one of these seconds with one of those. So we will have a total of 100 feet per second. Now, feet per second is a velocity, right? Acceleration is feet per second squared, but feet per second is a velocity. And now we're going to convert it to miles per hour. So we'll take our 100 feet per second, and there are 5,280 feet in 1 mile, and there are 3,600 seconds in 1 hour. What I'm doing is I'm knocking out all these variables here, these units of measure. So feet divided by feet, seconds divided by seconds. And what I have now is miles per hour. So we have 100 times 3,600, and so that is 360,000. So we'll get 360,000 divided by 5,280. And so we'll divide that, and we get about 68 miles per hour. All right. Kind of ran out of room for that one. But all right, a long-distance runner ran a race in 5 hours, averaging 6 miles per hour for the first 3 hours and 5 miles per hour for the last 2. How far did she run? So here we're gonna break them apart. So 6 miles for the first 3 hours. So we're gonna do 6 miles. We're gonna do 6 miles per hour times 3 hours, and that will give us 18 miles. And for the last 2 hours was about 5 miles per hour. So we're going to do 5 miles per hour times 2 hours. And that's going to be 10 miles. So together, we have 18 miles plus 10 miles equals 28 miles. So this runner ran 28 total miles in this particular race. Okay, so you're wondering, like, why are we doing what appears to be quite simple? Well, we're starting our first unit on antiderivatives, and in this chart, we'll start to get into a topic called integration. So let me go up. We would have done this in class here. I would have asked you, if we were in class, to approximate the area under these curves. And a lot of the times I get students that do different things. So they, for instance, will, count the blocks. They'll say, well, this whole thing right here is 1 unit because this is counting by 1/2. So be careful there. This is counting by 1/2. So they say, well, that's a unit. That's about another unit. So 1 by 1 is 1. This is probably another 0.75 of a unit. Okay. This might be another 0.5 of a unit up here. And then this might be another 0.5-ish or 0.25 of a unit. That's what students sometimes do. They also do something like this. They go, oh, well, it kind of looks like a triangle. So if I were to draw a triangle here, and I know that what's shaded is actually less than that. So the area of a triangle is 1/2 base times height. So area of a triangle is 1/2 times the base, which is 2, the height, which is 4. So the area of a triangle here is 4 units. But it's going to be less than that. So students will say, well, if that's 4, maybe it's somewhere, it's probably about then maybe 3 units. Maybe a little bit less. So that's what students do sometimes to determine the area that they see there. In this case, we could do another triangle. Let's do this one. It's going to be more than this triangle. So I'm going to do area, which is 1/2 base times height. Here we'll be given, we have 1/2 the base, which is 4, the height, which is 4. So it's 1/2 of 16, which is 8. So students would probably approximate this, the area as being about probably 10 or so, if you had to approximate. This one right here is perfect because we do have a base and a height. Everything works out great. We actually have a triangle, right? So the area is 1/2 base times height. The exact area here is 1/2 of 6 times 4. So the area of this triangle is 1/2 of 6, which is 3. 3 times 4 is 12. We know based on our geometry, that the area of this is definitely 12 units. Okay, this is much easier to calculate the area. Now, I haven't shown you, we'll get to this, but there is a way to exactly approximate this particular area here that is shaded under the curve of x squared. Okay, I'm going to do it right now. Let me think. Let me figure out. that area. So this is exactly going to be, I'm just doing some work in my head right now. Okay, this is exactly, the exact area is exactly 2 2/3 units, which is really cool. I'm going to show you how to get there eventually, but I don't want to right now. We're going to work up to it. We're going to understand what it is to use anti-differentiation to find that area. Let me see, the next one here is going to be exactly 10 2/3. So the area is exactly 10 2/3 for this one. So here we are. Now you have all of your areas for these. We would have done this in class, and I would have had you investigate it, but this is the best we can do for now. Okay? All right, so just to recap, you already did your assignments and your tests and everything in the CCA. So Unit 7 is done. We now are starting Unit 8. So Monday, which is today, your goal is to watch the notes for this section and then complete this particular worksheet, okay? It's the CUDA, LRAM, RRAM, MRAM, and trapezoid rule. And we'll meet Math Live tomorrow. And then you're going to rewatch the notes if needed. And you're also going to practice the Unit 8 Quiz 1 review. I'll post the quiz soon, probably today or tomorrow. So you'll have it a little bit early, but don't wait till the last minute. The only thing that's the assignments that are due on Friday are the Google Unit 1 quiz, the quiz review, and the CUDA worksheet. Okay, everything's in our notes, so you can either print them out, or if you want to handwrite it on a separate sheet of paper, you can, but then you'll just scan it and send it to me. I think we're going to try to submit these paper assignments on Google Classroom, and then these it will either be a Google form or a Go formative, okay, and that will be digital. All right, so let's go to our first example. So why are we starting this? Well, what's really cool is back in the day, we realized that we could use area to determine these items under a curve. So for instance, a train travels 80 miles per hour for 5 hours. Well, if we were to graph this on a graph, I don't think it's going to let me do that. If I were to put this on a graph, and I call this hour 0 and hour 5, and I call this 80 miles per hour, these are hours. If I were to graph this 80 miles an hour for 5 hours, and I don't know, I look at how much area is under this curve, well, that area right there is actually going to be 400 miles. So we can actually use area to determine our rates and our units, like miles. So 80 times 5, the area of that is 400, therefore it's 400 miles. All right, so that's what we're starting right now. So the need to calculate instantaneous rates of change led to the discoveries of calculus, to an investigation of the slopes of the tangent lines, and ultimately to the derivative, to what we call differential calculus. But derivatives revealed only half the story. In addition to a calculation method, a calculus, to describe how functions change at any given instant, they needed a method to describe how those instantaneous changes could accumulate over an interval to produce the function. And that is why they also investigated areas under the curve. And so that's our main focus today. We call that integral calculus. So instead of differential calculus, we now are starting what's called integral calculus. Newton and Leibniz had calculus for finding slopes, and the calculus for finding areas on the curves, two geometric operations that would seem to have nothing to do with each other, although they were connected. Okay, we call this discovery the fundamental theorem of calculus. So that's pretty much, we're going to highlight that, the fundamental theorem of calculus. That's the important part of today, along with integral calculus and areas under the curve. All right. So here you see our first example of distance traveled. So here you have from 7 a.m. to 9 a.m. a train traveling at a velocity of 75. So 75 times 2, because this has a difference of 2, is 150. Okay, that's super easy to calculate, but isn't this one a little bit more difficult? So that train traveling at 150 miles, because it's traveling at a rate of 75 miles per hour for 2 hours, that's easy to calculate because everything's perfect. But sometimes they won't be. So Leibniz and Sir Isaac Newton kind of came up with this idea of breaking this down into rectangles. So what we can do is we can quickly kind of calculate for a majority of these a really good approximation for what we see. Okay, wouldn't you agree that if I calculated this rectangle and this rectangle and this rectangle and this and so on and so forth, that we would get a pretty good approximation of what's happening under this curve? So that's our focus for today. Those are what we call rectangular approximation methods. Okay, this method in general is called a rectangular approximation method. We have 4 different kinds of them. One is what we call LRAM. One is what we call RRAM. One we call MRAM. And one of them you don't see yet, but we'll talk about it. Okay, let's focus on these 3 first. LRAM stands for left rectangular approximation method, or left hand. Left, do they use the word hand? Or, yeah, left hand, endpoint. So left hand rectangular approximation method. The next method we have is what we call the RRAM, and that is the right hand, the right hand rectangular approximation method. And the last one is what we call MRAM, which is called the middle or midpoint. I'm not sure what the textbook refers to it as. Oh, midpoint. They call it the midpoint. I've also heard it be used as the middle, but we're going to say midpoint rectangular approximation method. So you notice the same curve is in question, right? We have a graph of y equals x squared. The question is, what's the area underneath it? Well, before you did this problem, we did it as a warm-up. Here's x squared from 0 to 2. We approximated maybe 3 or so. We get an exact amount of 2 2/3. Our 2 founders of calculus, they studied a little bit more as using rectangles. So what they have here, and it looks like they broke it into what's called 6 equally spaced subintervals. Okay, so they did 0, 0.5, 1, 1.5, 2, and 2.5. Okay, what they did was they started at the left hand and they went to the right. So you'll notice that one of these triangles, rectangles, you can't even see because 0 squared is 0. So this one has no thickness or no height. I'm sorry, has no height. The next rectangle intercepts here, which is 1/2 squared. So it's graphing 1/4 units high, and it's 1/2 of a unit wide. This next one is 1 squared. Where am I squaring it? Well, that's the function they gave me. So what I'm going to do is I'm going to calculate all those separately. So this is 1 squared, which is 1. So it's 1 unit high, and then it's 1/2 a unit wide. This next one is 1.5 squared. This next one is 2 squared. And our final one is 2.5 squared. Okay, so these are my 6 rectangles, but we're working from what we call the left hand endpoint. So you see that endpoint, that endpoint, that endpoint, 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 and endpoint. So those are the endpoints in question. So what we're going to do, we're going to find how wide each interval is. So we are going to take the amount of intervals over the intervals. So we're going to do 3 divided by 6, because it's going from 0 to 3, and we want it divided into 6 equally spaced subintervals. So this is 0.5. This is what is sometimes referred to as delta x. So delta x is 0.5. The change, each one is 0.5. Okay? If I want to calculate these, what I'm going to do is I'm going to take each one of my rectangles. Each one of my rectangles is 0.5 wide, and then I'm going to multiply it by how tall it is, so 0 squared. So 0.5 times 0.5 squared, 0.5 times 1 squared, 0.5 times 1.5 squared, and then 0.5 times 2 squared, and 0.5 times 2.5 squared. What am I doing? Well, I am simply just doing the area of a rectangle, which is equal to base times height. So each rectangle, the area is base times height. I'm calling these units right here, I'm calling these units my base. They're all 1/2 units wide. And I am here, let me change the color because I think it makes more sense to maybe use, here's my base, that's an orange, because it looks like that's what I did above. And then these are my heights, which I believe I did in green, so let me just try to stay consistent. Okay, so the height of each rectangle is based on squaring. My endpoint is at those locations because x squared, that's what I'm doing. I'm just evaluating this x squared. Okay, if my function was different, I'd evaluate a different function. But for right now, x squared is what we got. So this is going to give me 0.5 times 0. It'll give me 0.5 times 0.25. You know what? Why don't I just do the math in my calculator, so to save room. So this is going to be 0. This is 0.125. Let me see. Yep, this will be 0.125. This is going to be 0.5. This one, we have 1.5 times 1.5 times 0.5. This is 1.125. This is 2 times 2 is 4. Half of that is 2. And then 2.5 times 2.5 times 0.5 is 3.125. Okay, what we're going to do now is add these all together. So the area of all of my rectangles is equal to plus 2 plus 1.125 plus 0.5 plus 0.125 is about 6.875. So LRAM is about 6.875. Nope, sorry about that. Mr. Hoffer, I'll call you right back. I'm making a video lesson. Okay, bye. Sorry about that. Let me mute my phone. Okay. So we get 6.875. Okay. Now that was an underestimate, I would say, because we look at all these gaps, right? We have this area not accounted for. We have a little bit of that area. We have a little bit more. We have a little bit more, a little bit more, and we have all of this not accounted for. So yeah, it's going to be more than 6.875. Remember, it's actually, we actually got, oh, we can't go with that number because it wasn't long. It's not as much. That our new interval here goes to 3. So that wouldn't work out for us. Okay, so let's do our next one. Let's do the right rectangular approximation method. So look at this. We're now working from the right-hand side. So we're doing 3. We're going to input 3, okay, and 2.5, and 2, and 1.5, and 1, and 0.5. So working from the right-hand side. Oops. We're going to work from the right-hand side today. Now. Okay. Let me just list all of these. Again, we should have 6 numbers because we have 6 intervals. Okay. And so now your rectangle has some height, your first one over there. These are going to be 3 and 2.5 and 2 and 1.5 and 1 and 0.5 and 0. But we're not going to use 0, right? We're working from the other side. See how we didn't use 3 on this side? Because 3 wasn't the left endpoint. Now 3 is the right endpoint. So what I'm going to do, I'm actually going to copy all this over to save time. Feel free to pause the video at this moment. But the reason why I'm copying and pasting, because almost all of our work will be the same. The one thing we're not going to use is this first one. We're going to erase this first one because we're not going to use that. I'm going to move all of this up because we're using all of these, but we're actually starting at 3. So maybe I should put these in a reverse order, but I think you can follow along. What I would have started with was 0.5 times 3 squared. And then I would have gone to 2.5. See, it would have worked from the right-hand side. So I would have done 3, 2.5, 2, 1.5, 1, and then 0.5. So yeah, these are in the reverse order, but to save time, then I am going to, whoops, let me erase this. Okay, to save time, let's just leave those numbers. And now the only other thing we have to do is find 3 squared, and half of that is 4.5. So I'm going to add these together. 0.125 plus 0.5 plus 1.125 plus 2 plus 3.125 plus 4.5. Hopefully I didn't make any mistakes, but I think I did this all good. So we get 11.375. So the right-hand approximation method gives me 11.375. Notice how different it is from 6.875. It's a lot more. 11.375. Okay, this is definitely a lot more. Notice it's an overestimate. We have all this extra, all that extra, all that extra, all that extra, all that extra, and then you can't even see it, but we overestimated that little portion that never hit the curve there. So this is an overestimate. This one is an underestimate. Guess what? We can do a little over, a little under, right? Here's a little bit under. This is a little over. Here's a little bit under. Here's a little bit over. A little bit under, a little bit over. Under, over, under, over. We can actually go with the middle of everything. So this is going to get a little bit messy, but let's just do our best with this. So we're going to use, let me just label this 0.5, 0, 1, 1.5, 2, 2.5. Well, where's the middle? Okay, so this is at 2.75. And this middle is at 2.25 and 1.75 and 1.25 and 0.75 and 0.25. So it's almost even too small to graph properly here, but we're going to use those numbers now. So it's called the middle or midpoint approximation method. We're going to the middle of the rectangle, okay? So we're not going to use 0 or 3 or 1/2 or 2.5 or 1 or 2 or 1.5. We're using what's in the middle of the rectangle. So I am going to copy this over, but we are going to have to do a lot of work here to change these numbers. Okay. Whoops. Let me see if I can move this over just a little bit. That's as far right as that will go. This appears to be as far left. And okay, so all these are going to go. All these values are going to change. Okay. Whoops. That's gone. That's gone. That's gone. All that's gone. And then these numbers are going to change because you know what won't change is how wide your rectangle is. That will always stay the same. Okay? These numbers are now going to become 0.25 squared and then 0.75 squared and then 1.25 squared and 1.75 squared and 2.25 squared and 2.75 squared. Remember, I'm squaring them because that's the function they're asking me. This will change. Don't just do the same process over and over. Do what the function says. In this case, the function is x squared, so it's saying just square it whenever you see an x. So that's going to be your output. But again, it all depends on what you're really given, okay? So let's see. 0.25 squared and times 0.5. We get, oof, this is rough. It's okay. 0.03125. Now we're going to do the next one. 28125. Let's hope this cleans up nicely. Next one is 0.78125. And I just hope I don't make a mistake, because then you'll be lost. 1.53125. Two point 53125. Yep. I just want to check my work. So yep. Just give me one more second. I want to make sure I haven't made any mistakes up to this point. 2.25 squared times 0.5. Okay, it looks pretty good so far. And then the last one, 2.75 squared times 0.5 is 3.78125. All right, so we're going to add these all together. So I'm going to do that one plus that one plus that one. And I'm just pulling these from my calculator. And wow, I get about 8.9375. Now, if I did everything right, let's see, 3, 4, 5, 6, 7.2, 8.4, 8.5, 8.6, 8.7, 8. Yeah, that looks good. 8.9375. So 8.9375. 8.9375. Okay? Those are the three methods. Pretty much those are the notes. I'm going to do a couple more problems. Let me tell you what this actual answer is. The exact answer of area under that curve is actually 9. So the area under this curve is exactly 9. Between 0 to 3, it's exactly 9 units squared. Oh, yeah, let's label all these units squared. Unit squared, and unit squared. So I would ask the class at this moment in time, which is your best approximation method, LRAM, MRAM, or RRAM? And, you would say, I would hope MRAM, especially because you now know that that's 9 units. And we came really, really, really close using MRAM. The margin of error was not that much at all. We're talking 0.0625. I mean, 0.0625 divided by 9 units is times 100. We're talking about 0.7% off. That's barely anything. So this is a great method to try to approximate area under the curve. Now, I don't want you to say all the time that MRAM is our best answer. On this one it was, but not every curve is MRAM going to be the best approximation. It just depends on what calculations we're doing. Does the curve increase or decrease? What's the interval between that we're looking for? How many sub-intervals do we have? There's a lot of factors that play into it. For the most part, the ones we do, MRAM will probably be the best approximation method, or a new method I'm going to show you later on. But this is pretty much it for for approximation methods. Okay, so you have your LRAM, your MRAM, your RRAM, and take a look. Oh, look at this! I actually included the fraction form that the textbook did, okay? So here they have what I called delta x, which is the width of everything, and they found it by doing 3 divided by 6. And look at this, 6.875, 8.9375, and 11.375. They actually did all of that work. They wrote it a little bit differently. Notice they wrote it in fraction form, and this is actually pretty easy to do in fraction form because when you're squaring 9/4, it's 81/16. So, it's actually easy to do if you don't have a calculator, and you can piece it all together. Now, some students might have already noticed, hey, do I need to write 1/2 every time I do this? Because think about what you could write this as. You could factor out this 1/2, and this 1/2, and this 1/2, and this 1/2. I think you're getting the point, right? So we factor out these 1/2s, and what you're left with now is 1/2 of 0 squared plus 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared plus 2.5, which is 5/2 squared. You can do that. That's fine. It actually saves you a little bit of time. Notice it's exactly what we did up here. We did our base times our height, right? Those are all our heights. So here you have your base. You still have your base out front here times all of your heights of all the different rectangles. Whoops. Okay, you can do that. So notice what they did as well. The textbook used a calculator to change their intervals. So instead of doing 6 like we did, so we did 3/6, which was 1/2, they did, hey, let's do 3/12, which is 0.25. They made every rectangle a 1/4 of a unit wide. Then they did this, 3 divided by 24. They made it 0.125 wide. So what they're doing is they're putting a lot more rectangles in that smaller space. They're making it not as wide. Look at this 3/1000. Look at what happens when it's 3/1000. So what conclusion can we make the more subintervals we have? And I want to give you some weight and thinking time for this one, but I would say that the more intervals, the more subintervals we have, and those are the subintervals, n, the more subintervals we have, the closer to the exact answer, the exact amount of area, we get closer to the exact area. Okay, remember the area is 9. So we get closer and closer to the exact area the more subintervals we have. I am not going to make you do more than like 4, 6, or 8. I think that's a lot. So we'll stick with like a low number. And you just have to make sure that you find out how wide your interval is based on your subintervals. Okay? So this one, example 1, we did above. Did this example above. Okay? It's the same thing, t squared, okay? And 0 to 3, we did. We just didn't break it into the amount of subintervals that they did. This would have been way, way, way too much, okay? Don't forget, this is what LRAM would look like in green. This is LRAM. In RRAM, it's what you see there, and MRAM is what you see here. So for that same rectangle, this is where RRAM would work from. Whoops. That's where RRAM would work from. Here, this is my MRAM, that same rectangle. We're not moving the rectangles. They stay exactly where they are, so don't move them. And then this is where LRAM would work from. Okay? Don't just break your rectangles up based on the bottom Don't move them around. Okay, so those are your three locations of your LRAM, RAM, and MRAM. Okay. All right, so you are already ready for the worksheet. The unfortunate thing is this worksheet only gives you the LRAM answers, okay? If you want to know the MRAM and RRAM answers, I can give those to you. And I will also show you trapezoid rule. Wait, did we do trapezoid? Do I ask for that? I do ask for that on the quiz review. Okay. Trapezoid rule, when you are... Here's the trapezoid rule. Ready for this? If I were to connect... Let me go back to this example. If I were to connect the triangle, the rectangles this way. Let's say I connected them this way. Okay? What I have is this figure right here. That is not a rectangle anymore, right? What kind of figure is it? Well, it is actually a trapezoid, right? Do you see that? Let me turn it. It's a trapezoid. Okay? So the trapezoid rule would say, these are right angles, okay? The trapezoid would say, here's your L1, here's your L2, here's your height, and the area of a trapezoid is L1 plus L2 over 2 times your height. Notice your height really is your interval down here, okay? So really it's your width. So your height now is your base, while your height, I'm trying to not make this confusing, but now that I'm saying it out loud, that's your base and this is your height for your trapezoid. Now this seems like a lot of work. It is not at all a lot of work. Look at what you're doing. You're averaging them. So guess what you're going to do now? Simply, very easily, average the two numbers you get for LRAM and RRAM. So the trapezoid rule, here's your trapezoid rule. It is equivalent to LRAM, because those are your left-hand sides, plus your RRAM, those are your right-hand approximations, all divided by 2. Because remember, LRAM and RRAM both have the 1/2, which is the width of your rectangle. Now it's going to be the width of your trapezoid, but it truly is the height of the trapezoid now. And so your trapezoid now is based on the left and the right-hand side because those are your L1 plus your L2. So for this example, the trapezoid rule would have been 6.875 plus 11.375 divided by 2. That is, it's super simple when you think about it this way. And I'm trying not to make it more confusing. I'm just showing you where the numbers are coming from. So we get 18.25 over 2. And that gives us 9.125. So the trapezoid rule, the trap of that same example from above, the trapezoid rule, the same example from here, would have given me just a little bit of an overestimate, a 9.125 estimate, okay? What that means is that when we connect these together, it actually was a little bit above the curve, okay? And so it just did a little bit too much. That's your trapezoid rule. Like I said, it's the average at LRAM and RRAM, and the reason why is because, let me rotate this. Whoops. For this example, L1 is my LRAM, so that the L1 is the left-hand side. RM is my right-hand side. The height is determined by delta x, right? So it's always the height is really the width now. So that's your base times your height, and I'm just averaging my heights, okay? So I'm going to put this back the way it was, and that's it. So here's what you need to do before Friday. Complete this worksheet and send it to me. I'm going to try to get Google Classroom up and ready for you to submit it there. Scanned copies, Adobe scan, whatever, pictures. Okay, so you want to do LRAM, RM, MRAM, and trapezoid rule for these. I'll try to make an answer key if I have time. Unit 8 quiz 1 review, there's already an answer key. So you're going to want to do this as well and print it and then send me a scanned copy. Okay? And that, for those three, that's, yeah, so there's 3 questions. So that's what's due Friday. And then you'll take a quiz, I think, on Go Formative for these questions. Okay? And that's all we have for this week. Do not wait till Friday to finish it. All right. With that, I will leave you. I'll leave you to get going. All right. Thanks, everyone. See you on Tuesday.